The moon has been mapped with astonishing precision. We know the heights of its mountains, the depths of its craters, and the chemistry of its soil. Yet beneath that familiar landscape lies a world we have never seen. In 2017, Japan's Selene mission confirmed a lava tube beneath the Marius Hills region, estimated to stretch for around 50 kilometers, protected beneath roughly 50 meters of solid rock. Scientists have also identified skylights, collapsed openings that lead directly into these underground chambers. They are real entrances into the moon's hidden interior. Inside, temperatures are thought to remain remarkably stable, while the surface swings through a range of roughly 300 degrees Celsius between lunar day and night. These caves may preserve geological records untouched for billions of years. They may contain valuable deposits of water ice, and they may become the safest place for future astronauts to live, shielded from radiation, micrometeorites, and the harsh extremes of the lunar surface. The mystery is no longer whether these caves exist. It is what has been waiting inside them all this time. We make these long form space documentaries because we love this stuff, and so do you. If you want to keep exploring with us, subscribe, and we'll be here whenever you need a quiet journey through the cosmos. To understand this, we need to go back to the moon we thought we already knew. The moon earned its reputation through familiarity. For generations, we watched the same face rise above our world, believing its story had already been told. Even after human footsteps reached its surface between 1969 and 1972, that confidence only deepened. We carried home images, samples, and memories. We also carried assumptions. Across 6 historic landings, astronauts explored 6 different locations and returned approximately 382 kilograms of lunar rock and soil. Every fragment transformed our understanding of the moon's age, chemistry, and violent past. Yet every single sample came from the surface itself. No mission drilled deep beneath the crust. No expedition entered the underground spaces that volcanic history may have left behind. That distinction mattered more than anyone realized. For decades, the moon seemed geologically complete. Ancient impacts had scarred its face, volcanic activity had long since faded, and the broad outlines of its history appeared settled. We believed we understood our nearest celestial neighbor because we had touched it. But touching the surface of a world is very different from knowing what rests beneath it. A different generation of spacecraft began changing that picture. The Japanese Aerospace Exploration Agency launched the spacecraft named Kaguya in 2007, carrying instruments designed to study the moon with remarkable precision. 2 years later, the National Aeronautics and Space Administration sent the Lunar Reconnaissance Orbiter into lunar orbit, expanding that effort with cameras, radar, and detailed mapping systems that reached beyond ordinary photography. The discoveries were subtle at first. Instead of revealing dramatic mountains or unfamiliar craters, the data hinted at something hidden below the visible landscape. Beneath plains that seemed unremarkable from above lay evidence of hollow passages preserved inside ancient volcanic rock. These were lava tubes, natural tunnels created when flowing molten rock cooled into a hardened roof while liquid material continued moving beneath it. Once the eruption ended, the remaining molten rock drained away, leaving an empty corridor sealed beneath the surface. The Apollo explorers could never have seen structures like these. Their missions unfolded entirely in the open, surrounded by landscapes exposed to space for immense stretches of time. Orbital instruments, however, could detect patterns impossible to recognize from ground level alone, revealing that the moon possessed an internal architecture almost completely hidden from view. But the greatest surprise was not simply that these tunnels existed. It was that they forced us to reconsider what exploration had actually achieved. We had mapped the exterior with astonishing detail, collected priceless samples, and built generations of scientific knowledge. Even so, those accomplishments described only the outermost layer of a far deeper story. As we continue our journey together, you are no longer looking at the familiar moon that hangs above Earth each night. You are beginning to see another moon entirely, one whose most remarkable landscapes have remained concealed beneath its own ancient skin. If you could stand above the moon more than 4 billion years ago, you would struggle to recognize the world beneath you. The familiar gray landscape did not yet exist. Instead, immense volcanic forces reshaped vast regions again and again, making the moon one of the most geologically active bodies anywhere in the inner solar system. The broad, dark markings that we see from Earth preserve that forgotten chapter. Early astronomers called these regions Maria, the Latin word for seas, believing they held water. They were looking at something very different. Each dark plain is an immense field of hardened lava spread across the surface after countless eruptions poured molten rock through fractures in the crust. These eruptions rarely resembled the towering explosions of Mount St. Helens or Krakatoa. Their lava was unusually fluid, flowing across enormous distances before finally cooling into solid basalt. Some individual flows stretched for hundreds of kilometers, which is about 62 miles, covering older terrain beneath layer after layer of volcanic rock until entire landscapes disappeared beneath fresh stone. The scale is difficult to grasp. One striking example is the basin called Mare Imbrium. It contains an estimated 4 million cubic kilometers of solidified basalt that is nearly 2,485,000 cubic miles. Even from orbit, the frozen remains of those eruptions dominate a large portion of the moon's visible face, preserving evidence of a world once driven by extraordinary internal heat. But volcanic worlds do not remain active forever. Earth continually renews itself through plate tectonics, the slow movement of enormous sections of crust that recycle heat and material deep inside the planet. The moon never possessed that same long lasting engine. Its smaller interior gradually lost heat. Its molten regions became increasingly limited, and each passing era left fewer opportunities for fresh lava to reach the surface. Eventually, the eruptions ended. The final confirmed volcanic activity occurred around 1 billion years ago. By then, complex multicellular organisms on Earth still had an immense evolutionary journey ahead before forests, dinosaurs, mammals, or human beings would ever appear. Throughout all of that history, the moon's volcanic landscape remained essentially unchanged, preserving the final products of its fiery youth. Those ancient eruptions created more than the plains we recognize today. As molten rock surged beneath cooling crust, natural passages formed within the flowing lava itself. Some remained open after the eruptions ceased, protected beneath roofs of hardened basalt that endured across unimaginable spans of time. These underground spaces were born remarkably quickly, sometimes over mere hours, days, or weeks, before becoming sealed away beneath the surface for ages beyond human comprehension. But once we understand the violence that shaped the moon, those hidden passages no longer seem unexpected. They become the natural outcome of a world that once burned from within, leaving behind an unseen landscape every bit as real as the one reflected in the night sky. Picture a river flowing beneath a layer of ice. The surface appears fixed and solid, while movement continues unseen below. Ancient lava behaved in much the same way, although the temperatures and forces involved were far beyond anything we encounter in ordinary landscapes. As molten rock traveled downhill, its exposed surface met the surrounding environment first. That outer layer cooled rapidly into solid basalt, creating a hardened roof that insulated the lava still moving underneath. The newly formed crust trapped heat remarkably well, allowing the interior flow to remain liquid even as the shell above continued thickening. The process became surprisingly efficient. Within this natural conduit, molten rock advanced much like water through a pipe, protected from rapid cooling by the very material it had already created. Fresh lava continued entering from the volcanic source, while older material flowed farther downslope through the enclosed passage. The tunnel itself was never carved into stone. It formed as the stone gradually built itself around a moving stream of liquid rock. Every eruption eventually reaches an end. Once the underground supply diminished, the remaining molten lava drained away under its own weight, continuing toward lower ground until little remained inside the channel. What stayed behind was an empty corridor, complete with a hardened floor, sturdy walls, and a solid ceiling. A lava tube is simply the hollow space left after the molten river has departed. We can still witness this remarkable process on Earth today. Active volcanoes across the Hawaiian Islands regularly produce fresh lava tubes during eruptions, and many have later been explored on foot after cooling completely. Some extend for several kilometers, which is about 1.9 miles, beneath the volcanic landscape, preserving the exact sequence of events that created them. But another force changes everything. Earth pulls downward with roughly 6 times the gravity experienced on the moon. That stronger pull places enormous stress on underground ceilings, limiting how wide most terrestrial lava tubes can safely become before the rock eventually gives way under its own weight. Their dimensions are impressive, yet gravity constantly imposes practical limits. The moon follows different rules. With only about 1/6 of Earth's gravity, those same basalt ceilings experience far less structural strain. A tunnel that would collapse almost immediately on our planet can remain stable for immense spans of time beneath the lunar surface. Scientific studies suggest that some lunar lava tubes may theoretically reach widths of several kilometers, that is nearly 2 miles, creating underground spaces so vast that familiar terrestrial comparisons begin to lose meaning. One region has drawn particular attention. The Marius Hills contain volcanic domes, winding lava channels called rills, meaning long trenches carved by ancient flows, and countless signs of intense volcanic activity. For many years, these features were fascinating geological clues. But among them rested one remarkable formation that transformed those clues into direct evidence, revealing that these immense underground passages were no longer theoretical ideas, but physical places waiting beneath the surface. From high above the Marius Hills, one feature refused to fit the surrounding landscape. It was almost perfectly circular, sharply defined, and unlike an ordinary impact crater. When Japanese Aerospace Exploration Agency images revealed it during 2009, researchers found themselves studying a formation that seemed to lead somewhere rather than end at the surface. Its opening measured about 65 meters across. Nearly vertical walls dropped into darkness, with no obvious floor visible from above. The geometry alone suggested that this was something fundamentally different from a crater created by an incoming asteroid. The explanation came from volcanic geology. Scientists identified the feature as a skylight, a natural opening formed when part of the ceiling above a buried lava tube collapsed. Instead of exposing solid rock below, the collapse uncovered a vertical shaft leading directly into the empty tunnel beneath. It was not a cave entrance carved by erosion or flowing water. It was a break in the roof of an already existing underground passage. That realization changed everything. Soon afterward, the National Aeronautics and Space Administration used the Lunar Reconnaissance Orbiter to examine the same location in greater detail. Higher resolution images revealed that the shaft descended approximately 40 meters before widening into a much larger underground chamber. Yet, even with improved imaging, the floor of that chamber remained hidden. Darkness absorbed nearly every trace of reflected light, preventing orbital cameras from seeing deeper inside. The Marius Hills opening was not alone for long. Researchers identified another confirmed skylight in the Mare Tranquillitatis region, located within 100 kilometers, which is about 62 miles, of the Apollo 11 landing site. This opening measures approximately 100 meters across and descends an estimated 70 to 80 meters before disappearing from view. A third confirmed skylight was later recognized within Mare Ingenii on the far side of the Moon, extending the pattern across widely separated volcanic terrain. Despite their different locations, all three share remarkable similarities. Each displays an almost circular shape, steep interior walls, and an absence of debris piled beneath the opening. That missing debris is especially revealing. If the cave floor sat close below, collapsed material would likely have accumulated into a visible mound. Instead, the shafts appear to continue well beyond the reach of orbital observation. Their surrounding terrain also shows no indication that these collapses happened recently, suggesting they have remained exposed for immense spans of lunar history. But even today, we cannot see beyond those openings. Light entering from above reaches only part of each shaft before fading into complete darkness. From orbit, nothing inside reflects enough illumination to reveal what lies farther below. We know these doorways exist. We know where they lead. Yet since their discovery, no robotic explorer, camera, instrument, or human visitor has ever crossed their threshold into the moon's hidden interior. Imagine trying to understand the inside of a mountain without ever touching it. You send a signal into the rock, wait for its return, and allow the echoes themselves to describe what human eyes cannot yet reach. That is precisely the approach scientists used to investigate the hidden landscape beneath the Marius Hills. The Japanese Aerospace Exploration Agency equipped its lunar spacecraft with an instrument called the Lunar Radar Sounder. Radar is a method of exploration that sends radio waves into solid material and measures the returning echoes after they encounter changes beneath the surface. Solid rock reflects those signals differently than empty space, allowing researchers to distinguish buried structures that ordinary cameras cannot detect. For years, the information remained preserved inside the mission's archives. Then, in 2017, researchers performed a fresh analysis of the radar observations and published their findings in the peer-reviewed journal called Geophysical Research Letters. Near the already confirmed skylight, they discovered an unmistakable echo pattern that matched the signature expected from a large, continuous underground cavity extending sideways beneath the lunar surface. The estimated dimensions were astonishing. The detected passage stretched for approximately 50 kilometers, which is about 31 miles. It measured roughly 100 meters across, stood about 50 meters high, and lay beneath a ceiling of solid basalt estimated to be around 50 meters thick. Instead of suggesting a collection of isolated chambers, the data pointed toward one immense corridor continuing through the ancient volcanic rock. Picture that scale for a moment. A tunnel, 50 kilometers long, which is about 31 miles, reaches across a distance comparable to Greater London from one side to the other. It also approaches the length of Manhattan Island, repeated several times in succession. Yet this enormous passage has remained sealed away since volcanic activity ended more than 1 billion years ago. But the discovery reached far beyond impressive dimensions. Scientists had already suspected that lava tubes existed because of the skylights visible from orbit. The radar measurements transformed suspicion into measured reality. They revealed the tunnel's approximate size, confirmed that its roof remained structurally intact across an extraordinary distance, and demonstrated that the underground space continued well beyond the collapsed entrance. Even so, the echoes remain incomplete. Radar cannot reveal whether the floor is covered with smooth basalt or broken boulders. It cannot determine whether smaller passages branch away into unseen networks. It cannot identify hidden deposits of water, ice, or other volatile materials, meaning substances that easily change from solid to gas under changing temperatures. It simply tells us that a vast empty space exists. But that single conclusion changed scientific priorities almost immediately. A stable underground corridor extending for 50 kilometers, which is about 31 miles, is no longer an interesting geological curiosity. It is a confirmed destination. And despite everything we now know about its existence, we still possess no direct observation of what occupies the darkness beyond its measured walls. Stand on the open lunar surface in your imagination for a single day, and the ground beneath your boots becomes an unforgiving machine driven entirely by the sunday. Nothing softens its rhythm. Nothing interrupts its extremes. Every cycle follows the same relentless pattern, repeated across billions of years. One lunar day lasts about 29 and one-half Earth days. That means nearly 2 continuous weeks beneath direct sunlight, followed by nearly 2 continuous weeks without it. Since the moon possesses no atmosphere, there is no blanket of air to hold warmth after sunset or reduce the intensity of daylight heating. The surface responds immediately. Under uninterrupted sunlight, exposed ground can reach approximately 127 degrees Celsius or 261 degrees Fahrenheit, easily hot enough to boil water under Earth conditions. When darkness returns, temperatures plunge toward negative 173 degrees Celsius or negative 279 degrees Fahrenheit. That is cold enough for carbon dioxide to freeze if an atmosphere actually surrounded the moon. Every cycle repeats. The difference between those extremes approaches 300 degrees Celsius or 540 degrees Fahrenheit. Any habitat placed on the open surface must survive that enormous thermal swing over and over again without structural failure. Every joint, every cable, every electronic system must endure expansion and contraction across a range that challenges even the strongest engineered materials. But temperature tells only part of the story. The moon also lacks a global magnetic field and an atmosphere. A magnetic field normally deflects many charged particles arriving from the sun, while an atmosphere absorbs much of the remaining radiation. Without either form of protection, the solar wind, meaning the constant stream of electrically charged particles flowing outward from the sun, strikes the surface directly. Cosmic rays arriving from distant stellar explosions also penetrate with little resistance. During powerful solar particle events, meaning intense bursts of energetic radiation released during solar eruptions, dangerous exposure levels can develop within only a few hours. Measurements taken on the lunar surface average roughly 1,369 microsieverts of radiation each day. That is about 200 times the typical daily exposure experienced on Earth. At that rate, an astronaut living continuously on the surface could approach career radiation limits within approximately 6 months. There is another challenge beneath every step. The lunar ground is covered by regolith, a layer of extremely fine fragments created through more than 4 billion years of meteorite impacts. These particles resemble powdered glass, clinging to equipment through electrostatic forces, wearing away seals, scratching protective visors, and presenting serious health risks if carried into living spaces and inhaled. But all these hazards share one remarkable weakness. A thick roof of ancient basalt blocks radiation, softens temperature extremes, shields against tiny incoming impacts, and separates living spaces from the abrasive surface. Long before human engineering imagined such protection, geology had already built it beneath the moon itself. Numbers can sometimes reveal a place more clearly than photographs. One measurement, collected from high above the lunar surface, transformed the way scientists understood these underground spaces without requiring a single machine to descend inside them. The National Aeronautics and Space Administration placed an instrument called Diviner aboard the Lunar Reconnaissance Orbiter. A thermal radiometer is a device that measures heat by detecting infrared energy naturally emitted from surfaces. Over many years, Diviner assembled the most detailed thermal map ever created for the moon, recording how different landscapes gained and lost heat throughout the long lunar day. One location stood apart. When Diviner examined the skylight in the Marius Hills region, it found that the visible floor near the bottom of the shaft remained close to -20 degrees Celsius, or -4 degrees Fahrenheit. Even as the surrounding surface passed through dramatic heating and cooling, that small area showed remarkably little change. This result came directly from observation. Scientists did not arrive at this value through computer simulations alone. The measurement came from an orbital instrument, repeatedly observing the same location over time. That distinction matters because it replaced expectation with evidence gathered from the moon itself. The explanation lies in the shape of the opening. The steep walls surrounding the shaft prevent direct sunlight from reaching its lowest visible surfaces during the normal progression of the lunar day. Thick basalt surrounding the cavity also acts as an effective thermal insulator, meaning it slows the movement of heat into and out of the rock. Together, these natural conditions create a protected microenvironment, a small region whose temperature behaves independently from the exposed terrain above. But the visible floor is only the beginning. If the connected lava tube extends beyond the shaft, as radar observations indicate, conditions deeper inside should become even less influenced by the changing environment outside. Scientists therefore expect those interior regions to remain similarly stable and perhaps even slightly warmer than -20 degrees Celsius or -4 degrees Fahrenheit, as the effects of the surface diminish with increasing distance. That stability carries enormous practical value. Inside the International Space Station, living areas remain near 21 degrees Celsius or 70 degrees Fahrenheit through continuous heating and cooling systems that consume valuable electrical power every hour of every day. The lunar cave achieves a consistent environment naturally, requiring no machinery to maintain its basic thermal balance. -20 degrees Celsius or -4 degrees Fahrenheit would certainly feel cold to any visitor. It resembles the interior of a commercial freezer rather than a comfortable room. Yet engineers can design reliable systems around one dependable temperature far more easily than around an environment swinging through hundreds of degrees. But consistency changes every calculation. In space exploration, predictable conditions reduce complexity, conserve energy, and improve long-term survival. The cave offers exactly that, not through advanced technology, but through geological processes that completed their work long before humanity ever looked toward the moon. Imagine closing the door to a room and leaving it untouched for 1 billion years. Even that comparison falls short because the environment beneath the moon has remained isolated on a scale that almost defies ordinary experience. Once those volcanic passages formed and the molten rock drained away, change nearly stopped. Very little could disturb them. There is no flowing water to dissolve minerals or reshape stone. No atmosphere carries wind-blown dust through the passages. No biological activity alters the surrounding rock. The moon also lacks the moving tectonic plates that continually reshape Earth's crust. Plate tectonics describes the slow motion of enormous sections of a planet's outer shell, a process that fractures, melts, and recycles ancient rock over immense spans of time. The cave walls simply endured. Basalt that cooled during the moon's volcanic era may still preserve the same mineral structure it possessed when it first solidified. Unlike exposed surface rocks, these underground walls remained protected from countless environmental processes that gradually alter chemistry and texture elsewhere. They have existed inside an extraordinary geological archive. Earth rarely offers such preservation. Ancient rocks certainly exist on our planet, yet they are exceptionally uncommon. The famous Acasta gneiss of northern Canada contains material dating back about 4 billion years, but those rocks have experienced repeated heating, crushing, and chemical transformation through Earth's restless interior. Much of their original character has been fundamentally altered by the planet that created them. But the moon followed another path. A section of volcanic basalt preserved within a sealed lunar lava tube could remain astonishingly close to its original condition after nearly 3 billion years. Locked inside that stone are isotope ratios, meaning the natural proportions of different forms of the same chemical element. These ratios act like enduring records, preserving information from the exact moment the lava cooled into solid rock. Some of those records are especially valuable. Scientists study the proportions of strontium, neodymium, and samarium isotopes because they reveal the temperature, composition, and evolution of the lunar mantle at the time each eruption occurred. Instead of offering indirect clues, the rock itself becomes a lasting record of conditions deep inside the moon billions of years ago. That history extends beyond the moon alone. The leading explanation for the moon's origin proposes that both worlds emerged after a colossal collision early in the history of the solar system when a Mars-sized body struck the young Earth approximately 4,510,000,000 years ago, because our planet and its companion formed from closely related material. Preserved lunar rocks provide a rare window into conditions that once existed inside the early Earth before billions of years of tectonic recycling erased much of that evidence. But that remarkable archive survives in only one place. Hidden beneath the lunar surface, untouched volcanic walls preserve a chapter of planetary history that our own world can no longer show us, waiting exactly where ancient fire left it. Among every resource that engineers hope to find beyond Earth, none carries greater value than water. It supports human life, can be separated into hydrogen and oxygen for rocket propellant, and is extraordinarily expensive to transport from our planet into space. Launching a single kilogram to low Earth orbit has often been estimated to cost around $20,000, making every naturally available source immensely important. We already know some exists. Water ice has been confirmed near the lunar poles, hidden inside permanently shadowed craters where sunlight never reaches the ground. Those depressions remain colder than -163 degrees Celsius, or negative 261 degrees Fahrenheit, allowing frozen deposits to survive across immense spans of time. But another possibility has steadily gained attention. Could the vast underground passages beneath the moon also preserve water? That question reaches beyond curiosity because the conditions inside those hidden spaces differ profoundly from the exposed landscape above. They combine darkness, thermal stability, and long term protection within an environment that has changed remarkably little since the moon's volcanic age. Scientists have proposed a plausible pathway. Across billions of years, countless comets and asteroids delivered water to the lunar surface. Individual water molecules did not necessarily remain where they first arrived. Instead, sunlight gradually released many of them from the soil, allowing them to migrate across the moon in a slow sequence of ballistic hops. Eventually, some encountered regions cold enough to trap them permanently. A cold trap is simply an environment where temperatures remain so low that frozen water stays in place instead of escaping back into space. A sealed lava tube could become one of the largest cold traps imaginable. Rather than a relatively compact crater, we are looking at an underground passage extending for approximately 50 kilometers, which is about 31 miles, protected from direct sunlight and buffered against dramatic temperature swings. Every characteristic already discussed points toward an environment where migrating water molecules could accumulate over immense periods. But observations from orbit added another important piece. In 2020, researchers reported in the journal Nature Astronomy that molecular water, meaning actual water molecules, rather than the related hydroxyl compound, exists across portions of the moon's sunlit surface. That discovery suggested water is more widespread and mobile than earlier models predicted, strengthening the idea that migration toward colder environments continues even today. Even so, an essential boundary remains. No spacecraft has entered a confirmed lunar lava tube. No instrument has sampled its floor. No mission has directly detected ice within a specific underground passage. The evidence remains indirect, built from established physics, observed temperatures, and the geological structure already revealed from orbit. But if frozen water waits inside the Marius Hills lava tube, the implications become remarkable. Instead of relying entirely on difficult polar terrain, where permanent darkness complicates construction and exploration, future explorers could find one of the moon's most valuable resources only about 50 meters, which is about 164 feet, beneath a confirmed opening in a far more accessible equatorial landscape. Imagine a microscopic passenger locked inside a fragment of rock, launched away from Earth by an impact so violent that the debris escaped our planet entirely. At first, this sounds like pure imagination, but decades of research have shown that this sequence belongs within serious scientific discussion, and it has become an active subject in the field of astrobiology, the study of life's potential throughout the universe. Large asteroid impacts are capable of accelerating surface rocks beyond Earth's escape velocity. Some of those fragments eventually cross the narrow gap separating Earth from the Moon before falling onto the lunar surface. Meteorites from the Moon have reached Earth through this same process, demonstrating that rocky material can travel naturally between neighboring worlds. The next question becomes more surprising. Could anything microscopic survive that journey? Laboratory studies and published calculations have indicated that certain spore-forming bacteria, organisms able to enter an extremely durable dormant state, could endure prolonged exposure to the vacuum of space, withstand substantial radiation during transit, and survive impact under favorable conditions. Survival would never be guaranteed, Yet the possibility remains scientifically defensible rather than purely speculative. But arriving on the moon would begin another challenge. Across the exposed surface, intense radiation from space steadily damages biological material. Without a protective atmosphere or global magnetic field, molecular structures gradually break apart. Over geological timescales measured in thousands to tens of thousands of years, any exposed biological traces would be expected to degrade beyond recognition. An underground passage changes that calculation. Above the confirmed lava tube lies approximately 50 meters of solid basalt. That immense layer of rock blocks most harmful radiation before it can reach the chamber beneath. The environment remains shielded, thermally stable, and largely isolated from the destructive conditions that dominate the surface. Preservation becomes a fundamentally different problem there than it is under the open sky. This does not mean living organisms inhabit lunar caves today. Instead, it identifies the lava tube as the one known lunar environment where biological material originating from Earth could, in principle, remain preserved across geological timescales. Even fragments of ancient organic compounds or dormant microbial structures would carry extraordinary scientific value because they might record information unavailable anywhere else. But that possibility introduces responsibility. Any mission entering one of these underground passages would need to follow planetary protection protocols, the internationally recognized procedures designed to prevent biological contamination of scientifically important environments. A spacecraft, a robotic explorer, or eventually a human visitor could unintentionally introduce modern microorganisms that obscure evidence preserved for immense spans of time. The challenge, therefore, extends beyond reaching the cave itself. Before people descend through a confirmed skylight, science must determine whether anything already preserved within deserves protection from the explorers who came searching. In that sense, the first footsteps into the moon's hidden interior may require restraint before discovery, ensuring that whatever history has endured, there remains as undisturbed as possible. Close your attention around a single moment. After everything we have explored, imagine that you have finally reached the floor beneath the Marius Hills skylight. The science remains unchanged, but now it becomes a place with dimensions, textures, and physical presence that your mind can begin to inhabit. The first sensation would be the absence of natural light. This is not the darkness of a windowless room or the fading light inside an earthly cavern. No scattered sunlight reaches this depth. No atmosphere softens the shadows. Unless a lamp is deliberately switched on, not a single photon enters your eyes. Human vision has no adaptation beyond that point, because there is simply nothing to detect. But the space surrounding you would be astonishingly vast. The confirmed passage is estimated to measure about 100 meters across, roughly the width of a 10-lane highway. Above you, the ceiling rises approximately 50 meters, that is nearly 164 feet, before disappearing into darkness. Ahead and behind, the tunnel continues beyond the reach of any practical beam of light, fading into a distance that cannot be measured by sight alone. Scale changes everything. Inside, a pressurized habitat built within that passage, sound would return for the first time since leaving Earth. Air would once again carry every spoken word, every mechanical vibration, and every footstep. Yet, the immense dimensions of the tunnel would shape those sounds in unfamiliar ways. Echoes could travel across hundreds of meters before returning. Certain tones might linger, while others fade unexpectedly as standing waves, meaning sound patterns that remain fixed between reflecting surfaces formed naturally inside the enormous chamber. Movement would also feel unfamiliar. Gravity on the moon measures only about one-sixth of Earth's strength. A person with a mass of 80 kilograms would weigh only about 13 kilograms there. Each stride would carry you farther than expected. A misplaced step would unfold more slowly, giving your body extra moments to react before reaching the ground. Familiar instincts would need patient adjustment. But every glance upward would draw your attention to a single remarkable feature. High overhead, the collapsed opening remains the only natural window connecting this underground world with the surface above. From the cave floor, that opening would appear as a distant circle suspended against the blackness of space, filled with unmoving stars beyond it. No human being has ever stood beneath such a view. It exists only as a possibility, waiting for its first observer. The air inside a habitat would still feel cold. Measurements near the skylight indicate temperatures close to -20 degrees Celsius or -4 degrees Fahrenheit. Comparable to the interior of a commercial freezer, that environment remains challenging, yet its remarkable quality is consistency. Unlike the surface above, where conditions swing between brutal extremes, the cave offers a stable world shaped by geology long before humanity ever looked toward the moon. Some of the oldest answers hidden inside the lunar caves may have nothing to do with their empty space at all. They may instead be written into the rocks themselves, preserved as an invisible pattern that no human eye can detect without scientific instruments. Today, the moon possesses no global magnetic field. Measurements collected during the Apollo missions, together with decades of orbital observations, confirm that the moon generates no protective magnetosphere surrounding the entire world. Unlike Earth, whose molten outer core still powers a global magnetic shield, the moon appears magnetically inactive on a planetary scale. But the rocks tell a different story. Many samples returned from the lunar surface contain remnant magnetism, meaning they preserve the direction and strength of the magnetic field that existed when the molten rock cooled and solidified. Those ancient minerals became natural recorders, locking their magnetic orientation into place billions of years ago. Their existence demonstrates that the moon once generated a magnetic field that later disappeared. Another puzzle deepens the mystery. High-resolution orbital images reveal graceful, bright patterns winding across portions of the lunar surface. These formations, known as lunar swirls, are especially striking at the Reiner Gamma region. They coincide with localized magnetic anomalies, isolated patches where magnetic fields remain stronger than the surrounding terrain, despite the absence of a global field. No single explanation has gained universal acceptance. Some researchers propose that powerful impact events altered the magnetic properties of nearby rocks. Others suggest these anomalies preserve fragments of the moon's original magnetic field within crust, possessing unusual mineral compositions. Both ideas remain under active investigation because neither explains every observed feature. But another possibility has emerged. Several magnetic anomalies occur near regions suspected to contain substantial subsurface volcanic structures. That relationship has encouraged scientists to ask whether the arrangement of buried basalt, including enormous lava tubes, influences the magnetic patterns measured above the surface. The connection remains unproven, yet it offers an intriguing direction for future exploration. Inside the Marius Hills passage, the cave walls may preserve a far more complete magnetic archive than any exposed outcrop. Shielded from harsh surface conditions, the basalt could retain the magnetic orientation established when each flow cooled roughly 3 billion years ago. Every section of wall would become a geological timestamp, preserving information from a particular eruption and a particular stage in the moon's internal evolution. Imagine collecting those measurements throughout a tunnel, extending approximately 50 kilometers, which is about 31 miles. Scientists could compare magnetic orientations from one location to another, gradually reconstructing changes in the ancient lunar magnetic field with a level of detail impossible to obtain from scattered surface samples alone. But the significance reaches beyond the moon itself. The history of its magnetic field reflects the history of its core, revealing when internal motion weakened, how cooling progressed, and how a once active interior gradually became dormant. Because Earth and the Moon share a common origin, those untouched cave walls may preserve clues about the earliest evolution of our own planet, still waiting within stone that no hand has ever touched. Long before anyone imagined exploring the moon's hidden passages, another investigation had already begun beneath its surface, almost unnoticed. Instruments left behind by visiting astronauts continued listening long after the crews returned home, collecting signals that would outlive the missions themselves. Between 1969 and 1972, the Apollo 11, Apollo 12, Apollo 14, Apollo 15, and Apollo 16 missions deployed seismometers across the lunar surface. A seismometer is an instrument that detects vibrations traveling through rock, allowing scientists to study an unseen interior by measuring the paths those waves follow. Together, these instruments formed the first, and still the only, seismic network ever operated on another world. The stations remained active until 1977. Budget reductions eventually brought the program to an end, and the instruments fell permanently inactive. Their recordings, however, survived. Vast archives of raw seismic data were carefully preserved, waiting through decades of technological change before anyone possessed better tools to examine them. But the information had never truly been exhausted. In 2022, researchers revisited the Apollo archive using modern machine learning algorithms, computer systems trained to recognize subtle patterns hidden within enormous collections of data. These methods proved far more sensitive than the processing techniques available during the 1970s, revealing thousands of seismic events that earlier investigators had never recognized. The moon became a more active place. Previously overlooked shallow moonquakes emerged alongside thermal moonquakes caused by the expansion and contraction of the lunar crust as temperatures changed. Deep seismic events also appeared more frequently than once believed, originating between approximately 700 kilometers, which is about 435 miles, and 1,200 kilometers, that is nearly 746 miles, beneath the surface. But those discoveries carried another implication. Seismic waves travel at different speeds through solid basalt than through empty space. Whenever those waves encounter a hollow chamber, their paths bend, weaken, or reflect in distinctive ways. By recording those changes from many carefully positioned instruments, scientists can reconstruct the hidden shape of underground structures without physically entering them. That possibility transforms the Marius Hills region. The original Apollo network consisted of only 4 widely separated stations, far too sparse for detailed underground imaging. Published studies indicate that a dedicated network of roughly 10 to 20 seismometers surrounding the confirmed skylight could generate a 3-dimensional map of the entire lava tube system, revealing its length, branching passages, sealing geometry, and internal connections with remarkable precision. Nothing comparable has yet been deployed. Nearly 50 years have passed since the last Apollo seismometer stopped transmitting. During that time, our methods for interpreting seismic information have advanced dramatically. yet the measurements needed to complete the picture have never been collected. We possess the mathematical tools, the computing power, and a confirmed destination beneath the surface. What remains missing is the listening network itself, arranged in the one place where hidden corridors are already known to exist. Sometimes discovery begins with seeing, but sometimes it begins by placing the right instruments in the right positions, then allowing the moon to tell its own story through vibrations that have been passing beneath its surface all along. Our view now widens beyond a single world. The tunnel beneath the Marius Hills is remarkable on its own, yet it also belongs to a much larger pattern unfolding across the rocky bodies of our solar system. Once we recognize how lava behaves under different conditions, familiar landscapes begin revealing similar signatures across enormous distances. Mars offers the next compelling example. Two orbiting spacecraft have searched beneath the Martian surface using radar. The European Space Agency's Mars Express carries the Mars Advanced Radar for subsurface and ionosphere sounding instrument, while the National Aeronautics and Space Administration's Mars Reconnaissance Orbiter carries the Shallow Radar Instrument. These systems send radio waves into the ground, then measure the returning echoes to identify changes hidden below the surface. Several volcanic regions have produced signals consistent with candidate underground voids. But Mars occupies an interesting middle ground. Its gravity is stronger than the Moon's, yet much weaker than Earth's. A structure that would collapse beneath Earth's stronger pull could remain stable on Mars, although not usually at the immense scales predicted for the Moon. Theoretical studies suggest Martian lava tubes could still extend for several kilometers, that is nearly 2 miles, across in favorable conditions, reflecting the extraordinary volcanic history of the planet itself. That history reaches its greatest expression on the Tharsis Plateau. Here stands Olympus Mons, the largest known volcano in the solar system, rising about 22 kilometers, which is about 13.7 miles, above the surrounding plains and spanning roughly 600 kilometers, which is about 373 miles, across. Eruptions from volcanoes of this magnitude could have produced underground lava channels unlike anything preserved on Earth today. The surface provides additional clues. Near Arzia Mons, long chains of collapse pits stretch across the landscape in remarkably straight sequences. Rather than isolated impact craters, these aligned depressions closely resemble collapsed skylights above buried lava tubes. Their arrangement suggests extensive underground passages whose roofs failed only at scattered points, leaving the hidden corridors concealed between the openings. But the pattern does not end with Mars. Radar observations gathered during the National Aeronautics and Space Administration's Magellan mission in the early 1990s revealed enormous winding channels crossing the surface of Venus. Some extend for thousands of kilometers, which is about 1,864 miles. Several researchers interpret portions of these remarkable formations as the remains of ancient lava tube systems, operating on scales that may surpass those preserved beneath the lunar surface. A broader principle gradually emerges where basaltic lava flows freely, cools from the outside inward, and later drains away. Nature repeatedly constructs underground passages. Gravity influences their final dimensions. Volcanic history determines their abundance, and time preserves or destroys them according to each world's environment. The same physical laws continue shaping very different planets. The moon therefore stands as something more than a nearby curiosity. It is the closest confirmed example of a geological process that may be widespread throughout the solar system, offering us a place where we can study a universal kind of landscape before seeking its counterparts on worlds much farther from home. Reaching the cave is not the greatest mystery before us. Reaching it safely is. 3 confirmed skylights already exist, each offering a genuine doorway into the moon's underground world, yet every one presents engineering questions that must be answered before the first explorer begins the descent. The Marius Hills skylight remains the best studied. Its surface opening measures about 65 meters across. Beneath that opening lies a nearly vertical shaft descending approximately 40 meters before widening into the larger cavern below. Orbital images reveal only the upper portion of this transition. Beyond that point, the geometry disappears into darkness because no instrument has ever observed the interior directly. But even standing beside the opening creates challenges. The rim is covered with regolith, the fine layer of powdered rock and glass produced by billions of years of impacts. Unlike solid bedrock, this loose material demands careful evaluation before anchors, cranes, or descent systems can safely transfer their loads into the ground. Every attachment point must remain dependable in an environment where repairs are exceptionally difficult. Communication presents another obstacle. Radio signals cannot pass through roughly 50 meters of solid basalt. Once a vehicle or crew enters the lava tube, direct contact with orbiting spacecraft and Earth immediately disappears. Any expedition, therefore, requires a communications relay positioned near the skylight, continuously receiving and retransmitting information between the underground explorers and the outside world. Then comes the challenge of seeing. The interior receives no natural illumination beyond the opening itself. Scientific work inside a passage approximately 100 meters wide and potentially extending for many kilometers, which is about many miles, demands powerful artificial lighting. Every lamp consumes electrical power, and every watt must be generated, stored, transported, and carefully managed throughout the mission. Finding your way becomes equally demanding. The moon has no navigation network comparable to the global positioning system used on Earth. Inside a lava tube, familiar landmarks visible from orbit vanish completely. Explorers must instead rely upon inertial navigation, which estimates position from measured movement, together with simultaneous localization and mapping, a technique allowing robotic or human explorers to build a map while determining their own location within that map at the same time. But descending into the shaft remains its own engineering discipline. No spacecraft or vehicle has ever been purpose-built for entering a lunar lava tube. Several proposed concepts use tethered descent platforms inspired by systems that lower deep-sea submersibles into the ocean, redesigned for vacuum conditions and the moon's reduced gravity. Such concepts remain carefully studied designs rather than completed machines. None of these obstacles violates the laws of physics. Comparable problems have already been solved in deep mines, underwater expeditions, and Antarctic research stations. Yet every solution must be redesigned for an environment unlike any of those places. The doorway already exists. The remaining task is building the tools capable of carrying us through it with the same care that revealed it in the first place. Long before any person steps beneath the lunar surface, the first explorers will almost certainly be machines. They are being designed for a place no wheel has crossed and no boot has touched, shaped entirely by the demands of an environment that remains unseen beyond a single opening. Among the most carefully developed concepts is the European Space Agency mission known as Descending and Exploring Deep Autonomy of Lava Underground Structures. Its robotic explorer, called Descending and Exploring Deep Autonomy of Lava Underground Structures, is designed as a sphere measuring about 46 centimeters across. That compact form carries stereo cameras for depth perception, light detection, and ranging instruments that measure distance using reflected laser light to construct detailed three-dimensional maps, radiation detectors, temperature sensors, and a tether system allowing controlled descent and possible retrieval from the shaft. Its shape serves a practical purpose. A sphere has no preferred orientation. If it rolls, bounces, or lands at an unexpected angle, every direction becomes equally usable. There is no front to lose, no roof to become trapped beneath, and no single attitude that prevents the mission from continuing after contact with the cave floor. But one robot may never be enough. The National Aeronautics and Space Administration conducted the Luna Cave Study, a formal engineering investigation examining how an expedition into the Marius Hills skylight could actually unfold. Multiple mission architectures were evaluated, including descent strategies, communications relay stations at the surface, methods for mapping the underground passages, and procedures for collecting samples that could eventually return to laboratories on Earth. Another idea spreads the work even farther. Researchers have proposed deploying numerous small robotic explorers together rather than relying upon a single machine. Each would investigate a different branch of the lava tube while passing information from one robot to the next until every observation reached a communications hub waiting at the skylight. Such a distributed network could gradually survey a passage extending for roughly 50 kilometers, which is about 31 miles, instead of remaining close to the entrance. Some concepts leave the floor behind entirely. One proposal imagines a robot attaching itself directly to the cave ceiling, traveling overhead instead of across loose regolith. From that elevated path, it could avoid debris fields, reduce encounters with unstable deposits, and maintain a broader perspective for mapping the surrounding chamber with greater efficiency. Yet every one of these machines currently exists only as studies, engineering drawings, computer simulations, and laboratory prototypes. Planetary science budgets must also support missions to Mars, the outer planets, and near Earth asteroids, forcing difficult choices between many worthy destinations. The Artemis program identifies lava tube exploration as an important long-term objective, but no funded mission presently includes entering one of these caves. The doorway has been confirmed. The robotic explorers have been imagined in remarkable detail. What remains is the decision to transform those designs into the first visitors beneath the moon's ancient surface. Imagine that the destination has finally been reached. Instead of raising walls against the moon, we begin with walls that have already stood for billions of years, waiting beneath the surface. That simple change in perspective reshapes nearly every engineering decision that follows. Engineers working with the European Space Agency and Foster and partners explored exactly this possibility through published lunar base architecture studies. Their conclusion was striking in its practicality. Rather than constructing a pressurized habitat on the exposed surface and surrounding it with enormous quantities of protective material, an inflatable habitat could be deployed inside a natural lava tube. The surrounding cave would already provide structural enclosure, shielding from radiation, and protection from extreme temperature changes without consuming additional construction resources. But the habitat itself would still be essential. The proposed design begins with a large, expandable living module lowered carefully through the skylight before inflation inside the cavern. The concept resembles the Bigelow Expandable Activity Module that was successfully tested aboard the International Space Station. Once expanded, the habitat becomes the pressurized environment where people live and work, while the surrounding basalt serves as a protective outer shell, that nature completed long before humanity considered visiting the moon. The strength of that shell matters enormously. Engineering calculations indicate that a basalt ceiling, approximately 50 meters thick, can remain stable across horizontal spans measuring several kilometers, which is about 1.9 miles, under the moon's reduced gravity. Strong volcanic rock, combined with weaker gravitational loading, produces conditions where carefully selected sections present a manageable collapse risk according to current structural models. That stability transforms an empty cavern into something approaching a ready-made foundation. Power introduces a different challenge. No sunlight reaches the cave interior, making direct solar generation impossible below ground. One solution involves compact nuclear fission systems, such as the National Aeronautics and Space Administration Kilopower Reactor, a 10 kilowatt demonstration successfully tested on Earth during 2018. Another approach carries electricity downward through cables connected to solar arrays installed around the skylight above. Food production follows naturally. Plants cannot survive without light, and basalt blocks every useful wavelength from the sunday. Proposed agricultural systems therefore rely upon highly efficient light-emitting diode grow lamps operating continuously inside dedicated cultivation chambers. Crop selection emphasizes varieties producing the greatest nutritional value for every unit of electrical power consumed, reducing demands upon the settlement's energy supply. But long-term survival depends upon more than engineering hardware alone. Research into closed ecological systems suggests that a genuinely self-sustaining settlement requires at least several dozen people with complementary skills, overlapping expertise, and fully redundant life support systems capable of continuing through unexpected failures. Such a community demands substantial living space, workshops, storage, laboratories, farms, and infrastructure. A lava tube stretching for roughly 50 kilometers, which is about 31 miles, offers room for gradual expansion that no surface habitat presently under serious consideration can realistically match. Beneath the moon, the architecture begins not with concrete or steel, but with geology that has already solved many of the hardest problems. Long before anyone builds a permanent settlement beneath the moon, another structure must take shape first. It cannot be seen through a telescope or mapped by an orbiter. It exists in treaties, diplomatic agreements, and the difficult question of who may use a place that belongs to no single nation. The foundation of modern space law began with the Outer Space Treaty, signed during 1967 by the United States, the Soviet Union, the United Kingdom, and many other countries that later joined the agreement. Its central principle remains remarkably clear. No nation may claim sovereignty over the moon or any other celestial body. National borders cannot simply be extended across space. But the treaty leaves an important question unanswered. It does not clearly explain how exclusive, long-term occupation of one specific location should be interpreted. A permanent settlement inside a confirmed lava tube might never declare ownership of the surrounding landscape, yet continuous operation, infrastructure, and restricted access could create practical control over one of the most valuable natural features ever discovered beyond Earth. That uncertainty has become increasingly important. During 2020, the National Aeronautics and Space Administration introduced the Artemis Accords, a framework now signed by a growing number of participating nations. Among its principles is the peaceful extraction and use of space resources. Although the accords reject territorial ownership, they acknowledge that organizations using local resources may establish operational zones that reduce interference with ongoing activities. In practice, the first functioning installation at a location could gain a lasting advantage through continued presence rather than formal possession. But other long term plans are also advancing. China, working alongside Russia through the International Lunar Research Station program, has outlined ambitions for a sustained human presence on the moon during future decades. Their planning documents have examined subsurface habitats among several possible approaches, recognizing the same engineering advantages that many international researchers have identified. Geography, therefore, acquires unusual significance. The Marius Hills lava tube combines several uncommon characteristics within a single location. Its immense confirmed dimensions, its position within the lunar middle latitudes, and its connection to the only directly measured subsurface void of this scale make it unusually accessible from a wide range of orbital trajectories. Those qualities increase its scientific value while also making it an attractive operational destination. No international race currently exists to occupy this cave. Yet once communications, equipment, power systems, transportation links, and living infrastructure begin operating inside such a site, replacing or relocating those investments would become increasingly difficult. Geography itself would reinforce that advantage. This situation differs from Antarctica, where international agreements established a carefully managed scientific commons with extensive legal precedent. The Moon has no equally mature framework governing long term occupation of specific underground environments, especially if they contain water, mineral resources, or strategic infrastructure. As we continue this journey, the cave becomes more than a remarkable geological discovery. It also becomes a place where science, engineering, law, and international cooperation will inevitably meet beneath the same ancient ceiling. The path toward a permanent home beneath the lunar surface does not begin underground. It begins with spacecraft already launched, missions already completed, and plans that are steadily transforming the moon from a destination into a place where people may remain. During November of 2022, the uncrewed Orion spacecraft completed the Artemis 1 mission, traveling around the moon before returning safely to Earth. That successful journey marked the first step in a program intended to return astronauts to the lunar surface for the first time since the Apollo 17 mission departed during December of 1972. But the objective reaches much farther than repeating earlier achievements. The ambition is permanence. Unlike the Apollo era, where every landing ended with departure, the Artemis program is built around infrastructure that survives between expeditions. Equipment remains in place, knowledge accumulates. Each mission prepares the ground for those that follow, allowing exploration to become continuous instead of temporary. One important element already planned is the Lunar Gateway, a compact space station that will orbit the moon. From there, crews, supplies, and scientific equipment can be transferred more efficiently to the surface. It creates a transportation hub rather than a destination. But Gateway cannot solve the greatest challenge awaiting every crew after landing. Life on the surface remains demanding. Current habitat concepts, developed by the National Aeronautics and Space Administration and the European Space Agency, are designed for missions lasting weeks or several months. Every structure standing beneath open space must carry its own radiation shielding, endure extreme temperature swings, and survive constant exposure to micrometeorite impacts. Those engineering requirements steadily increase both mass and complexity. But published mission studies increasingly point toward another architecture once expeditions extend beyond about 6 months. At that duration, accumulated radiation exposure becomes a growing concern for human health. A lava tube changes the equation by supplying natural shielding that no manufactured structure can easily match. Instead of transporting enormous protective barriers from Earth, explorers could use the surrounding basalt as an existing shelter while concentrating engineering effort on living systems, scientific equipment, and long term sustainability. The sequence follows a measured progression. Surface missions establish landing sites, communication systems, and reliable transportation. Robotic explorers then descend through confirmed skylights, producing detailed maps, environmental measurements, and engineering assessments. Only after those investigations reduce uncertainty would a crewed descent become a practical next step. Each phase depends upon the one before it. But that chapter has not yet received full financial support. Current Artemis mission manifests do not include a funded expedition into a lunar lava tube. The concepts exist within long range planning documents rather than approved flight schedules. Engineering studies continue, scientific interest grows, and the destination remains unchanged while priorities compete across many exploration programs. As we look across that unfolding timeline, the remarkable cave beneath the moon no longer feels disconnected from the present. Its entrance already belongs to an era that has begun. The spacecraft are flying, the infrastructure is taking shape, and each successful mission extends a bridge that gradually reaches from the familiar lunar surface toward a world below that has never known human footsteps. There comes a point when a place stops being only a destination and becomes a record. As we continue beneath the lunar surface, the cave gradually changes from a potential shelter into something even more remarkable, an archive written across immense stretches of time. The story begins long before the cave itself existed. Current scientific understanding holds that the moon formed about 4.51 billion years ago after a body roughly the size of Mars, known as Theia, collided with the young Earth. Vast amounts of molten debris entered orbit before slowly gathering into a new world. The event is known as the Giant Impact Hypothesis, and it remains the leading explanation for the moon's origin. Hundreds of millions of years later, volcanic eruptions transformed large regions of the lunar surface. Between roughly 4.2 billion and 1 billion years ago, enormous flows of basalt spread across ancient impact basins before cooling into solid rock. During part of that same immense interval, the earliest microbial life on Earth was beginning to appear, adapt, and eventually develop the ability to harness sunlight through photosynthesis. While our own planet was discovering biology, these cave walls were taking shape. But the rock preserved far more than its own existence. Locked inside the basalt are isotopic clocks, natural radioactive systems that change at precisely measured rates over immense spans of time. Rubidium gradually transforms into strontium. Samarium slowly becomes neodymium. By measuring the proportions of these elements, scientists can determine when the molten rock solidified and infer the chemical character of the lunar mantle that produced it. Each sample becomes a timestamp from deep within the moon. One measurement tells only part of the story. Imagine collecting carefully spaced samples along a tunnel stretching 50 kilometers, which is about 31 miles. Instead of examining one isolated outcrop, we would read a continuous sequence of volcanic history extending across an extraordinary geological landscape. Changes in mineral chemistry from one section to another could reveal how the lunar interior evolved over hundreds of millions of years, providing a level of temporal detail that scattered surface collections cannot easily achieve. But the significance reaches beyond the moon itself. Earth and the moon share a common beginning. Their interiors were shaped by many of the same early planetary processes. On Earth, however, plate tectonics continually recycles ancient crust into the mantle. Mountains rise and erode, oceans open and close. Much of our earliest geological record has disappeared beneath relentless renewal. The lunar cave escaped that fate. Protected beneath thick basalt for billions of years, its walls may preserve evidence of planetary evolution that Earth can no longer provide. A complete traverse through the Marius Hills lava tube, with carefully documented samples collected at regular intervals, would resemble reading an uninterrupted chronicle from an age that our own world has largely forgotten. In that sense, the cave becomes more than a passage beneath the moon. It becomes a journey through the earliest chapters shared by both worlds, preserved in stone until someone finally arrives to read them. Long before our own planet settled into the familiar world we know today, the moon had already begun preserving a history that Earth would eventually lose. As we follow the walls of this ancient cave, we are no longer searching only for the moon's past. We are approaching a record of the earliest chapters of the entire inner solar system. Earth has always been an active planet. Its crust shifts, oceans reshape coastlines, mountains rise before wearing away, and deep geological recycling steadily erases the oldest evidence of its beginnings. The moon followed a different path. Without plate tectonics or weather to continually remake its surface, vast portions of its ancient history remain where they first formed, waiting to be examined with modern tools. One of the greatest examples concerns a turbulent period known as the Late Heavy Bombardment. Between roughly 4.1 billion and 3.8 billion years ago, the inner solar system experienced an intense increase in asteroid and comet impacts. The heavily cratered lunar highlands preserve abundant evidence of this violent era. Comparable records on Earth have almost entirely disappeared beneath billions of years of geological renewal, leaving the moon as one of our most complete witnesses to that distant age. But the cave may preserve something even more detailed. Large nearby impacts could have blasted molten droplets of rock into the tube before cooling against its interior walls. These thin layers of impact melt glass would represent individual collisions rather than broad geological eras. If scientists identify and date successive deposits, each layer could become a precisely timed marker within a continuous sequence of bombardment extending across immense spans of lunar history. Such a record would complement the surface samples already collected without merely repeating them. Instead of isolated rocks gathered from scattered landing sites, researchers could study a preserved chronological archive protected beneath thick basalt. Every newly identified layer would strengthen our understanding of how frequently large impacts occurred and how the environment of the inner solar system gradually became less violent over time. But another possibility lies hidden inside the rock itself. As molten basalt cooled, small gas bubbles became trapped within it. These cavities, called vesicles, are tiny pockets formed when dissolved gases escaped from the lava before complete solidification. If some remained sealed for billions of years beneath the cave walls, they may still contain trace gases released during the moon's volcanic period. Those gases would provide an extraordinary glimpse into the brief, ancient lunar atmosphere created by volcanic outgassing before it dispersed into space. Nothing comparable exists within the Apollo collection. The 382 kilograms, which is about 842 pounds, of returned lunar material all came from exposed surface locations. For billions of years, those rocks endured direct contact with vacuum, solar radiation, and the steady bombardment of energetic particles. Their history has remained open to the environment throughout nearly their entire existence. A protected cave wall tells a different story. Imagine finding two identical books. One remained outside through endless storms, while the other rested inside a sealed archive. Both began with the same words, yet only one preserved every page. In much the same way, the hidden interior of the lunar cave may retain details of the early solar system that the exposed surface could no longer keep. Some places seem to exist outside the rhythm of history. As we linger beside this hidden passage beneath the lunar surface, the measurements and engineering studies begin to fade into the background. What remains is time itself, preserved in a form almost impossible to imagine. The lava tube was born during an eruption that probably lasted only days, or perhaps several weeks. Molten basalt surged through the channel before the surface cooled into a solid roof. Eventually, the flowing lava drained away, leaving an empty corridor beneath the hardened crust. From that moment onward, the interior entered complete darkness. Its temperature settled near -20 degrees Celsius or -4 degrees Fahrenheit. The surrounding rock became its shelter, and almost nothing disturbed it again. That moment belongs to an astonishingly distant world. When the cave finally sealed, the most advanced life on Earth consisted of microscopic single-celled organisms drifting through shallow seas. There were no animals with eyes, no brains capable of memory, no nervous systems complex enough to experience the landscape around them. The moon already possessed a chamber that would outlast civilizations before the first creature had ever looked across an ancient shoreline. But life continued its patient work. Over the next 3 billion years, multicellular organisms gradually appeared. Eyes evolved, nervous systems became more sophisticated, plants spread across dry land, vertebrates followed, dinosaurs rose, flourished, and disappeared. Mammals expanded into newly opened environments. Primates emerged. Much later, our own species evolved, perhaps around 300,000 years ago. Human communities eventually learned to observe the heavens, crafted the first telescopes, launched the first spacecraft, and placed astronauts upon the lunar surface. Decades afterward, radar instruments finally detected the hidden void beneath the Marius Hills region, confirming that the ancient passage still existed. Throughout every chapter, the cave remained unchanged. No breeze crossed its floor. No rainfall reshaped its walls. No flowing river carried away its record. The basalt ceiling continued to shield the interior, while countless generations lived and vanished beneath the distant blue glow of Earth. Geological time did not hurry or hesitate, it simply endured. But endurance can resemble waiting when viewed through human eyes. The cave never anticipated discovery because stone possesses no expectation. Yet, standing at the edge of this story, it becomes difficult to escape the feeling that an untouched place has accompanied the entire rise of complex life without ever joining it. Beneath roughly 50 meters of basalt, which is about 164 feet, the same corridor has persisted while nearly everything familiar to us came into existence above. We often describe remarkable places as ancient. That word usually feels sufficient until we encounter a span measured not in kingdoms or continents, but in billions of years. Here it begins to lose its meaning. Language was created to describe human experience, yet this hidden chamber belongs to a duration so immense that every civilization, every memory, and every written page becomes only the briefest moment beside walls that have remained exactly where they were since the deep dawn of our shared planetary history. Long before cities, agriculture, or written language, our ancestors had already discovered a simple truth about stone. Certain places offered protection that the open landscape never could. Those early choices were shaped by necessity, yet they also revealed a pattern that reaches far beyond Earth itself. Archaeological evidence shows that both modern humans and Neanderthals were using caves at least 400,000 years ago. They entered these spaces for practical reasons. Rock ceilings softened changes in temperature. Thick walls blocked wind and rain. Narrow entrances limited access for dangerous animals. A cave transformed an unpredictable landscape into one that could support life with greater security. The same physical principles now guide discussions about future settlements beneath the lunar surface. But shelter was only the beginning. As generations passed, caves became places where memory could remain. On the island of Sulawesi in Indonesia, artists painted wild pigs across limestone walls at least 45,500 years ago. Those images survived because the cave protected them from sunlight, weather, and countless destructive forces found outside. People who stepped into those chambers experienced complete darkness, enclosed spaces, and echoes that lingered after every sound. Their surroundings influenced both survival and imagination. Many thousands of years later, another remarkable cave preserved another chapter of humanity. The painted chambers of Lascaux in France, created roughly 17,000 years ago, remained hidden beneath layers of earth until modern discovery. Stable temperatures, chemical isolation, and protection from the changing seasons allowed pigments to endure with astonishing clarity. Had the same paintings been exposed on an open hillside, rain, frost, sunlight, and erosion would almost certainly have erased them long ago. The lesson extends beyond archaeology. Those identical conditions, darkness, environmental stability, and protection from constant change, also preserved the geological history inside the lunar lava tube. On Earth, caves safeguarded the traces of human creativity. On the Moon, they safeguarded billions of years of volcanic history. The subjects differ completely, yet the underlying physics remains remarkably consistent. When the surrounding world changes, enclosed stone often preserves what the surface gradually loses. But perhaps the deeper connection belongs to us. The earliest people entered caves because the world beyond them was difficult to endure. Future explorers may descend beneath the lunar surface for the very same reason. The distance between Earth and the Moon is about 384,400 kilometers, which is about 238,855 miles. The span between the oldest known cave paintings and the first permanent settlement beneath the lunar surface may exceed 45,000 years. Even so, the engineering challenge and the ancient human instinct point toward the same solution. Across immense distances and unimaginable stretches of time, the logic never truly changes. Gravity differs, atmospheres differ, landscapes differ, yet stone continues to offer stability where exposed ground cannot. The first families who gathered beneath earthly rock ceilings, and the first crews who may someday live beneath lunar basalt are connected by more than history. They are responding to the same enduring laws of shelter, proving that wherever humans travel, the safest place often begins beneath the surface. History often remembers a single name, even when thousands of people helped make the moment possible. After decades of mapping, engineering, testing, and planning, one individual will eventually stand at the rim of a lunar skylight and prepare to descend into a place no human has ever entered. That person is almost certainly alive today. Given the present sequence of robotic exploration, surface infrastructure, and later crewed expeditions, the first explorer of a lunar lava tube is likely now in their 20s or 30s. They may already be training as an astronaut, studying geology, mastering robotics, or learning how to solve problems in places where every decision matters. Their future role has not yet been assigned, yet the path leading toward that descent is already taking shape. But the final approach will unfold with remarkable simplicity. A pressurized suit will be checked one last time. Tethers will carry both weight and communication. Instruments will confirm every connection. Then the slow descent begins. The opening above measures about 65 meters across, and the vertical shaft extends roughly 65 meters, which is about 213 feet. That is nearly 65 meters. Before widening into the larger chamber below, artificial lights will sweep across basalt walls that have reflected no illumination for approximately 3 billion years. Every meter downward will reveal surfaces that have remained beyond human sight since the lava drained away. Eventually, the floor appears. Under 1/6 of Earth's gravity, each movement becomes measured and deliberate. Fine regolith may cover parts of the basalt where material gradually settled through the skylight across immense spans of time. Beyond the reach of the suit lamps, the passage continues in both directions. The known tube stretches for about 50 kilometers, which is about 31 miles, while much of its interior remains unseen. The darkness ahead is no longer an abstract scientific prediction. It has become a real landscape surrounding a living observer. Looking upward changes the perspective once again. Far above, the shaft forms a circular window cut through the moon itself. Within that opening lies a small piece of the sky filled with distant stars. It is the only natural break in the ceiling of an immense underground passage. From the cave floor, the universe is framed by stone rather than open space, creating a view that no camera has yet recorded. But discovery begins with careful routine, not celebration. The first hour will follow a disciplined sequence developed through years of preparation. Radiation levels will be measured at multiple locations. Temperature readings will be collected from the floor, surrounding walls, and higher elevations. Three-dimensional laser mapping, meaning a method that measures distance with pulses of light to build an accurate digital model, will document the chamber in extraordinary detail. The first wall samples and the first regolith samples will be sealed for return. One image still does not exist. A human figure standing inside the moon, looking upward through a circle of starlight. For approximately 4,510,000,000 years, this world has never known the presence of life within its hidden interior. One day, that will change. Some discoveries expand your view until the familiar becomes almost impossibly small. Others narrow your surroundings until every layer of stone carries the weight of unimaginable time. Human exploration has already revealed the first experience. The second still belongs entirely to the future. In 1987, author Frank White gave a name to a transformation repeatedly described by astronauts. He called it the overview effect. Those who looked back upon Earth from space often spoke of the same unexpected realization. National borders disappeared. Continents became part of a single living world. Against the vast darkness beyond, Earth appeared fragile, shared, and astonishingly small. The journey outward altered how many explorers understood the place they had left behind. But what happens when the direction is reversed? Instead of climbing higher above a planet, you descend beneath another world. Instead of seeing an entire globe suspended in space, your vision contracts into a chamber enclosed by basalt. Rather than endless horizons, there are rock walls shaped approximately 3 billion years ago. Above your helmet rests a ceiling many tens of meters thick, separating you from the stars. Beyond the reach of your lights lies an environment that has never reflected the gaze of another living creature. The contrast reaches beyond scenery. The overview effect emerged from overwhelming openness and extraordinary distance. A descent into a lunar lava tube offers the opposite experience. It surrounds you with enclosure, permanence, and geological persistence. Every surface speaks of time measured in billions rather than thousands of years. Every sound comes from your own movement. Every step carries the awareness that life has entered a place where life has never existed before. Researchers who study confined environments on Earth have examined the psychological effects of deep caves, polar research stations, submarines, and other isolated habitats. Those investigations suggest that unusual surroundings can reshape attention, memory, and perception in subtle ways. Yet none of those places remained sealed throughout nearly the entire history of complex life. None combines profound isolation with the knowledge that the surrounding rock formed before animals, forests, or flowers had appeared on Earth. But no published research can describe the exact thoughts of the first person who enters such a chamber. There is no experimental record. No interview exists. No journal has yet captured the first impression of standing beneath a lunar ceiling while the distant universe shines through a single opening far overhead. The language for that moment has not been written because the experience itself has not entered human history. The overview effect reshaped how many astronauts understood Earth without anyone intending it to happen. The lunar cave may offer another transformation born from exploration alone. This time, the lesson may come through enclosure instead of vastness, through ancient stone instead of endless sky, through the realization that you are sharing a space with 3 billion years of preserved history. Whatever changes within that first explorer will become the only evidence we have. Until then, the experience exists only as a possibility, waiting beneath the surface of the moon. If we step back far enough, the lunar cave becomes something larger than a destination. It becomes another chapter in a pattern that stretches across the entire human story, one repeated long before rockets, telescopes, or written history existed. Again and again, our ancestors crossed boundaries whose interiors could not be known from the outside. They sailed beyond coastlines that disappeared behind the horizon. They ventured toward frozen poles that no community had permanently occupied. They descended into the deepest oceans and climbed into the upper atmosphere. Eventually, they crossed the space between worlds and placed human footprints upon the moon itself. Science has always traveled with those journeys. So has strategy. But neither explanation fully accounts for why exploration persists across civilizations separated by thousands of years and vast distances. Knowledge matters, resources matter, yet there remains another impulse, one that appears whenever a frontier changes from imagined to reachable. Once a path exists, someone eventually chooses to follow it. The history of exploration repeatedly illustrates this pattern. In 1960, Jacques Piccard and Don Walsh descended into Challenger Deep, reaching approximately 10,929 meters, which is about 6.8 miles, beneath the Pacific Ocean. Engineers had calculated the crushing pressure awaiting them, but calculations alone could never substitute for direct observation. Their bathyscaphe entered an environment no human had previously experienced. There, against many expectations, they observed living flatfish and other organisms in a place once assumed to be nearly lifeless. Nature had preserved details beyond the reach of every previous model. But another example arrived less than a decade later. Before the Apollo 11 landing in 1969, scientists still debated how the lunar surface would behave beneath a spacecraft. Some worried that the blanket of fine regolith might fail to support the lunar module, allowing it to sink dangerously after touchdown. The mission proceeded despite those uncertainties. The surface proved stable, and another unknown became established knowledge through direct experience rather than prediction alone. The lesson reaches beyond those individual missions. Every unexplored place contains realities that distant observation cannot completely reveal. Instruments measure, models estimate, images inform, yet the interior of an undiscovered environment almost always carries details that emerge only after arrival. The universe consistently proves richer than the maps we create before entering it. That is where the lunar cave now stands. It is close enough for mission planners to design practical expeditions. It has been confirmed through orbital measurements. Its dimensions allow realistic engineering studies. Yet no human or robotic explorer has crossed its threshold. We know enough to prepare, but not enough to finish the story from afar. Perhaps that is the most revealing part of all. When you look across oceans, continents, planets, and now beneath the surface of another world, the pattern remains remarkably consistent. Our species does not simply observe horizons. We cross them. Each frontier eventually becomes the starting point for another journey, and the cave beneath the moon belongs naturally within that long inheritance of exploration. Some structures endure because people preserve them. Others endure because the universe never needed our help in the first place. The lava tube beneath the Marius Hills belongs to the second kind, existing on a timescale that stretches far beyond every civilization humanity has ever imagined. Our own future is tied to a much larger clock. The sun still contains approximately 5 billion years of hydrogen fuel before it exhausts the supply that powers its present state. Only then will it begin expanding into a red giant, transforming the inner reaches of the solar system. Throughout most of that immense span, the moon will continue circling Earth in a stable orbit, slowly drifting farther away through the steady exchange of tidal energy. For almost all practical purposes, the stage beneath our feet will remain in place. So will the cave. Its ceiling could collapse only if struck by an impact powerful enough to shatter an enormous thickness of basalt. But events of that scale have become increasingly uncommon as the inner solar system has gradually cleared many of its largest wandering bodies over the past 4 billion years. Small impacts still occur. Large ones remain possible. Yet the probability of a catastrophic collapse continues to decline across geological time. That changes how we should think about this place. Human beings usually define a resource as something consumed. We mine it, burn it, harvest it, or transform it. The lava tube asks for none of those things. It already exists. It requires no construction, no maintenance, and no continuous source of energy simply to remain what it is. It offers protection through its own natural architecture. In that sense, it resembles an inheritance more than a possession. Our greatest monuments reveal the scale of ordinary human ambition. The pyramids have endured for thousands of years. Roman aqueducts still stand after millennia. Great cathedrals have watched generations come and go beneath the same stone vaults. We rightly admire those achievements because they push the limits of craftsmanship and imagination. But each belongs to a span of history that barely registers against the lifetime of this cavern. The lava tube formed roughly 3 billion years ago. If its structure remains intact until the sun enters its final stages, it may persist for another 5 billion years. Against such a measure, the interval from the first shaped stone tool to the present becomes almost impossible to distinguish. Entire civilizations appear and disappear within an instant of geological time. But perhaps that perspective is the true gift. Every so often, ordinary physical laws create something astonishingly durable. Molten rock cools, gravity holds, time passes, no intention guides the process, yet the result survives long enough for an intelligent species to discover it. The cave was never shaped with humanity in mind. It emerged from flowing lava, governed only by physics, billions of years before the first human existed. That it now offers exactly the shelter, stability, and preservation we seek is not evidence of design. It is evidence that, on rare occasions, the universe leaves behind an inheritance that waits long enough to be understood. There are places that feel distant simply because they lie beyond our daily experience. Then there are places that remain distant even after we have learned their names, measured their dimensions, and traced their outlines from orbit. The lunar cave belongs to the second kind, resting at the edge of what humanity understands, yet already standing within reach. On average, the moon lies 384,400 kilometers away, which is about 238,855 miles. Light crosses that distance in about 1.3 seconds. A spacecraft completes the journey in roughly 3 days. Human beings have already traveled there within living memory. The path is no longer hypothetical. It has become part of our history, but history has so far remained above the surface. Beneath that familiar landscape, inside a tunnel formed when the solar system was less than half its present age, extends a passage approximately 50 kilometers long, which is about 31 miles. Since molten rock drained away and its ceiling hardened, no natural light has reached its interior. That uninterrupted darkness began before the first eye evolved in Earth's ancient oceans, before any creature possessed the ability to look upward toward another world. What then is truly hidden inside? The answer changes depending upon the question we choose to ask. A geologist finds pristine basalt walls preserving the history of a young moon. A planetary scientist sees evidence capable of refining models of the early solar system. Engineers recognize the safest known environment for long-duration habitation, protected from radiation, extreme temperatures, and constant micrometeorite impacts. Future settlers may discover deposits of water ice able to support human life. Researchers searching for ancient material from Earth may encounter preserved fragments delivered across space billions of years ago. Every answer carries weight, but another answer lies beneath them all. The cave represents a threshold. Throughout history, each generation has encountered one. Mariners faced the edge of incomplete maps. Explorers crossed into the Antarctic interior. Aviators climbed toward the upper atmosphere. Astronauts stepped onto the lunar surface. Before each crossing, the boundary appeared to define the limits of what could be achieved. Afterward, it became the beginning of another chapter. This threshold is different only in location. Its existence has been confirmed, its dimensions have been measured. Mission planners have incorporated it into serious engineering studies. Robotic explorers have been designed specifically to enter it. Yet neither machine nor human has crossed that boundary. The opening remains exactly where orbital observations first revealed it, connecting the familiar surface to a place no living creature has entered. But science reaches its natural limit at that point. It can calculate the descent, predict the environment, estimate the discoveries, and prepare every instrument with remarkable precision. Beyond the rim, however, observation gives way to experience. Whatever waits inside will become fully known only when someone stands there, looks outward from beneath the moon itself, and transforms the final unknown into part of the shared human story. Imagine arriving only after every calculation has ended, every descent has succeeded, and every careful step has brought you to the floor below. The journey no longer asks whether the cave exists. It asks only what it feels like to stand within a place that has endured almost beyond imagination. You lift your gaze. Above you rises a shaft carved through basalt, its walls climbing roughly 40 meters before opening into a circle approximately 65 meters across. That opening is the only natural break in the ceiling of a tunnel extending nearly 50 kilometers, which is about 31 miles. Far overhead, the stars appear within that circular frame as though the universe itself has been reduced to a distant window. Sometimes another sight would share that opening. If the position of the moon, the earth, and the observer align, our home world hangs above the shaft, blue and white against black space. From this distance of about 384,400 kilometers, which is about 238,855 miles, every ocean, continent, and cloud belongs to the only inhabited planet humanity has ever known. Everything familiar occupies a small portion of the sky, viewed from inside another world. Below your boots rests ancient basalt dust. A thin covering of regolith may blanket portions of the floor, gathered gradually through countless ages as tiny fragments drifted inward from the opening above. The surrounding rock remains steady at approximately 20 degrees below 0 degrees Celsius, or 4 degrees below 0 degrees Fahrenheit. Behind many meters of stone, radiation falls dramatically compared with the exposed surface, while micrometeorites can no longer reach this protected interior. Nothing moves. No wind crosses the passage, no weather shapes the walls, no natural sound has ever traveled through this chamber because no atmosphere has carried one. The space has remained undisturbed since molten lava withdrew, leaving behind a stable refuge that endured while life transformed an entirely different world. But this moment still belongs to the future. Parts of the required technology already exist. Other systems continue to advance through engineering studies and planned exploration. Several missions must come first before a human descent becomes possible. Somewhere on Earth, the individual who will eventually make that journey is living an ordinary day, unaware that history may one day remember a single careful step beneath the lunar surface. For all of recorded civilization, the moon has watched over changing generations. We marked seasons beneath it, crossed oceans by its light, filled stories and calendars with its presence, and finally walked across its plains. We mapped its mountains, collected its rocks, and photographed nearly every landscape visible from above. But one place has remained beyond every footprint. Its entrance has been found. Its dimensions have been measured. Its promise has been recognized. Deep beneath the familiar surface waits a chamber shaped by ordinary physics, preserved across billions of years, and ready for the first living visitor.